So good morning everyone. Let us welcome today Dr. Aneesh Mundayandan, Assistant Professor, School of Basic Science, IIT Bhubaneswar. And today he is going to uh, deliver a talk about linear algebra via complex analysis. So let me say a few lines about Dr. Anish. He is a PhD from IIT Kanpur in 2016 in the area of operator theory. He has been awarded gold medal for achieving the first rank in his BSc Mathematics from Kannur University in 2006 and received merit cum mean scholarship from IIT Kharagpur during his MSc in 2007 to 9. He qualified both for CSIR NET and GATE examination in 2008. He has obtained the postdoc fellowship from the National Board of Higher Mathematics in 2017 and visiting scientist fellowship from ISI Delhi and Bangalore in 2015 and 17 respectively. Earlier, he has served as an assistant professor at NIT Calicut on ad hoc basis in 2016-17, and he has published 7 research articles in peer-reviewed journals and has attended several conferences and workshops. So once again, I welcome you, Dr. Anish. So for the today's webinar of SOAWAL, so you can please start your talk on the topic you have given, linear algebra via complex analysis.
So
Thank
yeah,
you, Dr. Abhijit.
Thank you, Professor Manjula Das, for this introduction, and also I thank SOA University for inviting me for this talk, and in particular I thank Dr. Sutra for arranging this talk, and it's in fact my pleasure to give a talk. So and sorry for the inconvenience because it was scheduled for an early before 1 month. So because of some issues, so for that again I regret. And the title actually is given to algebra. One of you has to unmute, I think. Professor Manjula Das, can you please unmute? I think that's it.
Yeah, sorry?
Can you please unmute? Maybe that is reflected.
Okay, okay.
Okay. So the title is the earlier title was linear algebra via complex analysis, but then I had the slides, I lost the slides, so now that there is a change in the topic. It's now chaotic linear transformations. We all know what is Dr. Sutradhar. I think I can go ahead, right?
Yes,
Yeah, yeah.
could you please hold the mic in front of your face?
Mike, yeah. So am I audible now
Yes,
properly?
yes, yes,
Okay,
yes,
okay,
clearly.
okay. So I'll talk about chaotic linear transformations. Chaotic linear transformations. I'll show you the calculations and all those things. We all know what is linear transformations. Transformation which some sort of which respect some sort of linearity from vector space to another vector space. That is linear transformation. And in the underlying space, if you have a metric structure, linear structure plus a distance metric structure, which is metric linear vector space or topological vector space, and then we can talk about uh, chaos and other cyclic properties of linear transformations. So far we know that if you have come across nonlinear chaos, nonlinear dynamics and chaos, you might have seen that nonlinear maps, certain nonlinear maps exhibit chaotic property. Something linear means straight away linear. You may not have that chaotic behavior. Everything is very easy to predict. But contrary to this, we will now show that uh, linear, despite linearity, linear transformations on certain topological vector spaces. That means vector space additionally together with a topological structure, they can be chaotic. They can be as chaotic as nonlinear maps. That's what the today's theme. So let me. So I hope now I am audible properly. Let me share my OneNote.
Any problem?
No problem. I'm just sharing actually.
Doctor,
Yeah.
yeah.
Yeah. So is this visible? I just share chaotic linear transformations I wrote here. Is it visible?
On the screen, it is
Sutradhar?
written Dr. Anish is present.
Yes,
Then you
it
show
is,
the byte.
it is like
Yeah.
about to present, but actually the slide is not visible.
No slide. I just shared my OneNote where I wrote chaotic linear transformation. Is it visible? I think
It
it's
is
not.
not visible. It's not
Just
visible.
a minute. Okay. Yeah, I think it's now visible. Sutradhar, is it okay now?
Yes, yes.
Yes. So
It
this
is
is the
okay.
type. Yes. Chaotic linear transformations. Let me write what precisely what I am going to do. So the aim of the talk is aim. So the aim of the talk. So in general, uh, chaotic behavior. I'll tell you what CAO behavior is exhibited by nonlinear maps. Nonlinear maps. Okay. So this we know. We will come to know what are they. Just like such as nonlinear maps, such as the map x going to 4x into 1 minus x on the interval 1, the map z going to z square on the unit circle in the complex plane C. So maps like this are chaotic, and these you can see that they are non. Uh, I can hear some echo. Can you please?
Dr. Anish,
Yeah. Yes. Yes.
just let me ask, uh, is everybody able to see the slide
Yeah. Sure.
presentation?
Yeah.
I'm asking everyone,
Oh, maybe I
are all
don't
of you
know.
able to see the
Uh,
presentation?
it is visible. It is visible.
Yes, it is
Visible?
visible to me.
Okay,
Visible.
okay, 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 thank you.
Okay. Okay. Fine. Yeah. So maybe actually I request all to unmute because I hear a lot of echo. So it's a little bit disturbance for me. So whenever you like to ask, of course you can ask. So while I am presenting, please unmute. Okay, so maps like this, x going to, I'll come to this. I'll explain. X going to 4x into 1 minus x on the interval, close interval 0, 1, and z going to z square on the unit circle are chaotic. So now, so these are chaotic. I'll tell you why these are chaotic. Now, if you see 4x into 1 minus x, a non-linearity, x into x square. Here, of course, is doubling, so there is a non-linearity. Nothing is linear. I mean, not like alpha z plus beta. Okay, so and many other examples known for chaotic maps. they are non-linear. Now what we are going to show, despite linearity, despite the linearity, linear transformations can also be chaotic. This is what we want to show. Even though some maps are linear transformation, they can be chaotic. So I have to explain what is this terminology, this chaos, all those things. So chaos means you cannot predict in the long-term behavior of a system. That's the meaning. So again, more precisely, what I will prove, I'll take the linear vector space, something called the Banach space. This space, more precisely, we will consider the space, the space LP is equal to the set of all sequences x1, x2, so on. This each xi is a complex number. And what is, so a member in LP is actually a sequence. And what is the special thing about the sequence? This is absolutely p summable. That is xn to the power p, n equal to 1 to infinity. This series is convergent. So we consider this space LP. It's actually sequence space. Members in LP are sequences. They're every member will look like this. And what is additional condition on that sequence? That terms xn, they should satisfy this. P absolutely summable in the sense n equal to 1 to infinity modulus of xn to the power p less than infinity. Now there is a p, this depends on p, so I just wrote for L power p. And what is p? P ranges from 1 to infinity. I'll take I'll exclude p, I mean, because we have to take p less than infinity, 1 less than or equal to p less than infinity. And some of you, if you are coming from analysis background, then so we'll consider this LP and we'll show that, and we will prove that multiples of the backward shift, multiples of the backward shift operator, which is actually linear transformation. This backward shift is actually linear transformation. Shift operator, that is multiples, that is some scalar c, complex number c into the backward shift c, modulus of c bigger than 1, are chaotic. So this is the on LP. This is the aim of my talk. So here my aim is to show that if you take mod c bigger than 1, then c times backward shift on LP are chaotic. 1 less than or equal to p less than infinity. So first let me tell you what is chaos.
Dr. Anish,
Yes. Yes.
could you please precisely write the expression operator B,
Okay. Okay.
backward shift operator?
Backward shift operator. Yeah. So this is operator actually. OPE. Okay. So, or in other words,
I'm just asking, please.
Yes.
Please write the expression so that audience can understand. Write the expression of
Right.
B,
Yeah.
please.
That's I'm coming to this. So if you hear what is B, B from
Yeah.
LP to LP is the map. Is the linear map defined by B of, it should take a vector here, that is x1, x2, so on. And what is the map? It will just shift back. That is why it is called a backward shift operator. Backward shift is, so elements in LP are sequences of this type. So when you operate B on this, again you should get. at an element in LP. So what it just shifts back. X1 will disappear, X2 will come to the first position, X3 will come to second position, so on. So this will be X2, X3, X4, so on. So this is called backward shift operator B on LP, and we will prove that when mod C is bigger than 1, the C is a complex number, and mod C is bigger than 1, then C times B is a chaotic linear operator on LP. So this is so despite linearity, linear maps can also be chaotic. And if I have time, I'll show you that there are other examples of linear maps which are chaotic. So let's define what is chaos. So the meaning of chaos is, see, for instance, you take this is the definition. I suppose most of you are coming from analysis or at least background in analysis, so you can follow these things. F from X to X. X is some you can take it to be a matrix space, or so F from X to X is a given map. So X is any matrix space, or if you have any confusion, then just take X equal to Rn or close interval 0, 1, like that. You can take. So it only thing is F has to be a map from X to X. Okay. So F has to be a map from close interval 0, 1 to itself, or F is map from Rn to Rn or real line to real line, so on. So F is a given map, then F is said to be chaotic. F is said to be chaotic if on these two conditions. There are three conditions. The third one actually automatically follows from first two. Oh, so I will omit that. So F is to be chaotic if there is an element in the domain space S such that the orbit of X, which is defined as S, Fx, F of F square X, so on. So orbit of X is defined like X, then operate F on X, and you get F of X, then operate F on F of X, that is denoted by F square X, so on. So there is some element in X, small x, whose orbit, which is this sequence, is dense in X. And the second condition is the set of all periodic vectors, the periodic point, the set of all periodic vectors of are also dense, are also dense in X. Now there's a third condition which actually is called sensitive dependence on initial conditions, but I will not explain that. The thing is 1, 2 will imply the third condition to state that. Now I have so F is said to be F is a map from X to X. X is just a matrix space, or you can take X to be R, or the closed interval 0, 1, closed interval -1 to 1, or the unit circle in the complex plane. Just take that. Then F is said to be chaotic if these two conditions are satisfied. One, there should be there exists at least one element in X whose orbit, this is called the orbit of X under F. X and map I mean, its image F of X, F square. The notation F of F square X means F of X. The image of image of F of X under F. So this is called, I mean, F and F2X is called second iterate, F3X will be third iterate, and so on. So if there is a vector, there is an element X in capital X whose orbit is dense in X. Second thing, the set of all periodic now periodic points of F are also dense. So I need to explain what is the meaning of density, denseness, and what is the meaning of periodicity. So these two, if a function satisfies these two conditions, then we say that f is chaotic on x. And what does that mean? So it pictorially it means like this. Suppose your set is like this, okay, and somewhere you take a open ball, some set like this. Then the density means you can find an element x. When you iterate this element x, it keeps visiting, keeps roaming through the space x. This f of x will be here, f square x, cube x, so on. So density means a subset of x is called dense if its closure is x, or in other words, if x is metric space, every member in space y can be approximated by a sequence set A. Or in other words, this sequence will come arbitrarily close to every member in X. So that is the meaning of density. So this means first condition means you have a element here X. When it is iterated, it keeps visiting, it keeps roaming, or it comes close to every element arbitrarily close. So that is the meaning of the first one. Second one is set of all periodic vectors is dense. So again, it will come close. I mean, if here somewhere you can find a vector y, which is periodic. Periodic means y is called a periodic point. Y belong to x is called a periodic element if periodic element for f if f power some p x is equal to x. So you keep iterating, at some stage it is actually equal to the beginning. That's the meaning. F power p x is precisely equal to x. Then you call x as a periodic element, and the smallest p for which fp x equal to x is called the period of x. So the second condition says that you collect all the periodic elements of f. That means all points for which f power something of that element is equal to that element. Then such that collection is a dense set. That means you take any point arbitrarily close to that point, you can find a periodic vector. So what it says, first one says that there is some x which when iterated it visits everywhere, it roams everywhere in the space. And second condition says that close to that point you can find a periodic vector. Periodic vector means if you iterate this y, its orbit is just periodic. F power p x equal to x for y equal to y for some p. So in other words, behavior
Dr. Anish,
behavior of f cannot be predicted. The long behavior of f cannot
your
be.
voice
Yeah.
voice is breaking in between.
Yes.
You can put off your camera.
Connection right. Camera is on.
No, you can off the video.
Yeah. Is it
That
okay
might
now?
be helpful.
Yeah.
Yeah.
Is it okay?
Thank you.
Yeah. 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 Okay. So this is the definition of chaotic map. Function of chaotic map. F from x to x is a given map. X, you can take x to be a metric space, or in simplest case x is a real line R or closed double 0 1. Then f is said to be chaotic if you can find some element in x whose iteration is dense. That means the sequence x f of x f square x or 1 will come arbitrarily close to every point in the set, given set x. Second condition is the set of all periodic elements of f that is also dense. The set of all periodic is dense. So 1 and 2 will, geometrically it says that when you take a point, say x or y somewhere here, say somewhere here, then say suppose Z is the point or U is the point U, then if you keep iterating, its long-term behavior cannot be predicted in the neighborhood. So that's why the name chaotic. Now let me give you one example. What is the meaning of so so the example I will use here is this thing. Take f of z is equal to z square. Now f is defined from t to t. What is t? T is nothing but the set of the unit circle complex plane mod z equal to 1. So if you have the function f from t to t is well defined because when you take z from t, its square is also modulus 1. So it's actually well defined on the unit circle. T is nothing but the unit circle in the complex plane. So this is nothing but t mod equals set of collection of all points in the complex plane, all elements whose modulus is 1. So let us take f of z equal to s square, f z square. Then f is okay. So we have to see that. So if you go back to the definition, we have to make sure that f satisfies these two conditions. There is an element whose orbit is dense, that means it will come arbitrarily close to every other element, and then the set of all periodic elements is also dense. That means if you take the set of all periodic elements, that set, I mean, to near to every point, there is a periodic element. So we have to make sure. Now, to prove the first one, what we will do, we will use a theorem. It's easy to use that theorem without proof. So to prove that f is chaotic on the unit circle, we will use this theorem without proof. This theorem is called Birkhoff's transitivity theorem. Birkhoff transitivity theorem. So it's sometime in 1920s or 29. By the way, this chaos. Uh, actually, there are different notions of chaos accepted in literature, but this particular one is due to uh, an American mathematician Devani. He, sometimes in 1950s or 60s, he postulated this. Motivated by physics. Okay, so we'll to prove that this map f z equal to z square on the unit circle in the complex plane is chaotic, we will use Birkhoff transitivity theorem. What does this say? Again, here we have f from x to x. Okay, then the following is true. The following holds. There exists an element in X whose orbit x f of x f square x so on is dense in X. This means there is some element x in capital X so that this orbit comes arbitrarily close to every other in the space if and only if. So here X is a space, or in case if you're not familiar with terminology, you can assume X to be R or close to 0, 1, the unit circle like that. Only thing is X is a complete matrix space, so you can assume X to be R 0, 1, tau, then this little p which we define, etc. So there is some element small x whose orbit is dense in X if and only if for any two open balls for any two open balls b1 and b2 in the power sum k b1 intersection b2 is not equal to 5 for some k. So if from x to x is given, it's a function, x is a complete metric space, so you can take it to be close to 0, 1, the unit circle, so on. Then there is an element capital X whose orbit is dense. That means whose orbit comes arbitrarily close to every other element, even only if for any two open balls B1 and B2, fk B1 intersection B is not equal to it's not empty. Not equal to 5 is not empty. Now function satisfies property for any open balls B1 and B2. There is some case for which fk iterate B1 intersection B2 is not equal to 5. This is called transitivity. F is called transitive map. That's why this theorem is called Birkhoff transitivity theorem. This notion is called transitivity. So, proof without, I mean, I will take it granted without proof. So we take it granted. Okay. So no, again, what it says? It says that for any two, that means for every, any means every, I should write here every two open balls. So this means take any open ball B1 and another open ball B2, any two. Then if you keep iterating this ball B1, then at some stage, this will at stage fk B1 will intersect set B2. That's the mean. So this theorem says that rather than iterating a single, rather than finding a dense orbit, a single vector, single element, it's enough to consider iterates of open balls. Is it okay? Subhadar, is it okay? Am I audible?
Yes, you're audible, but your voice is breaking many times.
Yeah, maybe connection issue. It's also raining here.
Yeah.
Yeah. Okay.
We can understand. Please go ahead.
Yeah. So
Thank you.
So that's the meaning. This theorem says that instead of iterating a single vector, single element, and asking for its density, it's enough to consider arbitrary open balls, and then consider the iterates of an open ball, then see that intersects every. So here open ball means in a metric space, open ball is like say B. B is called an open ball around center some element x, radius epsilon means set of all points y in the space x which are at a distance maximum epsilon, distance x y less than epsilon. So this is the meaning. So open ball with center at x and radius epsilon. So this is the meaning of open ball in a metric space. Now we will apply this theorem to show that this function f of z equal to z square defined on the unit circle t is actually chaotic. So what we have to do, we have to prove that f has the periodic points are dense. They visit everywhere, arbitrarily close to every element in the unit circle. And secondly, that is the second condition. And the first condition was that it has a dense orbit. Again, Birkhoff transitivity theorem ensures that in order to prove that f is if it has a dense orbit x, f x, f square x, so on, it's enough to prove that for any two open balls or open sets, fk b1 intersection b2 is non-empty for some k. So we'll apply this. So we apply to the function f of z is equal to z square. So to see the t is the, what does f of z equal to z square does? It actually doubles. If you take z equal to e power I theta theta ranges from 0 to every member in the circle can be written as z equal to e power theta. Then f z is what? It's actually e power 2 theta, I 2 theta. So if I take z here, then see the angle, then this goes to 2 theta. So this arc, if I take this particular arc, if I take, this is mapped to doubling. So this angle will be doubled. So this will be mapped to this big arc. Okay. So we can easily see that. So since f of z equal to z square, the argument, that is complex argument of a complex number z, what we can see is that we see that if j is an arc, say let me take this arc, I will take this arc j. If j is an circle D, then j is equal to the entire circle after certain stage, after certain. Okay. Because doubles, next time when you take that iterate the arc, the angle double, so at some stage it will be the air circle. So we see that from this argument we see that there's transitivity theorem. In that theorem, uh, uh, for any two open arcs. Now in here open ball means open arc. There is a k for which fk b1 intersection b2 from t. So this implies f is having a dense orbit via the Birkhoff's theorem, via Birkhoff's transitivity theorem. So we got first f is put f we have proved via Birkhoff's transitivity theorem that f has a dense orbit. Now what next is have proved the set of all periodic points of f are dense.
Due to internet connection issue, the speaker has left us. I'm connecting with him. Please wait. The speaker is trying to join us. Please wait a minute.
These are the difficulties in
Yeah.
online
So
system.
is it okay now? Am I audible?
Yes, you are
Yes.
audible.
Yeah. Just let me.
Please share your
Yeah.
slide.
Right. I suppose it is now. Okay. So
Your slide is not visible yet.
the whole periodic points by definition this is okay.
Yeah, now it is visible.
It's visual, right?
Yes.
Yeah. Okay. Yeah.
Please go
So
ahead.
set of all z belonging to the unit circle for z to the power p is equal to for some integer p, positive integer p. So this means the set of all periodic vectors, periodic points of f ultimately depends on the roots of unity. Because if you cancel now, this is z is non-zero because it is on the unit circle. So z to the power 2p minus 1 equal to 1. So so what we have is uh, it's enough to prove now, to prove that set of all periodic vectors, periodic points of f is also dense. It's enough now to prove that the sets of the set of all roots of unity is dense, and which is clear. I'll tell you why in the circle. So so you take the circle. This is my unit circle, mod z equal to 1, which is in the complex by t, and center is here. What are the roots of first roots of unity? Z square equal to 1 if I take, then it's actually 1 and minus 1. So they are lying here. Next, if I take z cube equal to 1, then we have 3 roots. They'll be like here, here. Each dense 2 pi by 3. Next, if I take the roots of unity, then they are lying one here, here, I. So next is divided like this. Angle is getting reduced. Okay. Next, if I take z power 5 equal to 1, again the angle between the roots will be increased. If continues, as up certain stage, power some percent or equal to 1, the roots will be roots of the equation z power equal to 1. They will be distributed on the circle, and the angle between any two roots will be very less. So we see that from this argument, we see that roots of unity are actually dense in the unity. So once we have roots of unity dense in the unical, we have periodic points of f are dense. Together with the transitivity, we have f of z equals z square. The doubling map, it's actually chaotic on the unicircle. So this is one example. There are many more. And more intrinsic or extrinsic properties of work maps. I'll tell it not
Dr.
suppose
Anish?
without proof. Another example is this thing. Here we take f of x equal to 4x into 1 minus. Yes.
Yeah. Your voice was
What happened?
voice was
Okay, okay,
absent. Unable to.
okay,
We were
okay,
unable to listen to you for a long time.
okay.
Yeah. Please continue. Oh, oh.
I am unable to see the screen. Is it true for everyone?
Yes, yes. This speaker has left us again. Uh, I'm trying to connect him. please wait a minute. The speaker is trying to connect us. The speaker is continuously trying to connect with us. Dr. Anish stays in Patrapada itself. The weather is very bad there. Yeah. Please, Dr. Anish, please unmute your mic. Google Meet mic. Please unmute your Google Meet
Yeah,
mic.
so a lot of
Yes.
inconvenience mainly because of this network issue.
Yeah.
Maybe since we are, yeah, okay. So let me share it again.
Yeah.
So is it okay now? Is it visible?
Yeah. Clearly audible and visible also.
Okay, fine. Yeah. So now we come to the final result that we consider LP space set of all sequences. Members in LP are of the form. They are sequences of this form. And what is special about that sequence? They are P absolutely summable in the sense n equal to 1 to infinity modulus of xn to the power P less than infinity. Here we have to take 1 less than or equal to P less than infinity. You can take P less than 1 also, but then it will not be a Banach space. But we take 1 less than or equal to P less than infinity. Now we come to the final thing that we just saw 2-3 examples of nonlinear maps which are chaotic. Now we will take the backward shift. Backward shift, I just pointed out LP to LP. This is defined as B of, take a sequence, a member in LP, x1, x2, x3, so on. Now this is shifted back, x2, x3, so on. So this is the backward shift. Okay. Now, if you compute the norm, there is something called norm of, if I take member as x, then norm of p of x, you can easily see that this is the norm of x for each x in LP. So what it says that norm of p of x is less than or equal to norm of x norm of x. So this will be norm of b using boundness b. Bnx is less than norm of x for each x. Hence bnx, this orbit of x under the backward shift b, it's actually lying in the unit with the radius norm of x. So hence the sequence cannot be dense in LP. So since we want an orbit, so whatever x you take in LP, this orbit cannot be dense in the sense that this closure cannot be the full space LP. So since in chaos we want a dense orbit, it automatically follows that B cannot be chaotic. Now the situation will be very different if I multiply with a C with the modulus C less than. So what we want to prove, this is the main result I want to show you. Main result that C times B from LP to LP. B is the backward shift, C is a scalar with a modulus bigger than 1 equal to 1. C from LP to LP, modulus C bigger than 1 is chaotic. So this is what I want to prove. So you see that in previous examples, the functions are non-linear, but here you see B is a simple linear map on LP, the vector space LP. And C is multiple C. So to prove the main result, again I will say a criterion for chaos without proof. Criterion for chaos, just like the previous C from x to x is a given function. Here x you can just take like a topological vector space with a metric, or simply like you can take as LP. And suppose there exists a dense set. Dense means the set will not be close to every next dense set D in X and map S from D to D. So E from X to D, then suppose I can find dense 1.
Dr.
Summation
Anish,
Tnx
your
and
slides.
summation Sx n equal to 1 to infinity, n equal to 1 to infinity. These are versions.
Your slides.
Yes,
Your,
sir.
your slides are not visible again.
Just a minute.
Yeah.
Is it okay now?
Mm, not yet visible.
What about now? No, I think that's
Mm,
yes.
no, not yet so far. Dr. Anish, are you trying to share the video
Yes, I'm
slide?
trying to share. Yes. But actually, see what I can do. Connection is slow, so I'm actually using mobile data. That may be the reason.
Yes.
Yeah, so I just shared it again. Can you see that? So, Sutradhar?
Mm, not yet.
No. I think
Not
then it's
yet.
better to stop because already audience may be also getting slightly bored. So I can come to the conclusion that this C times backward shift is chaotic.
Yeah, it is now visible.
Right. Oh, is it visible? Okay, okay.
Yes, and you may conclude also
Yeah, I'm
if
concluding
you
it. Just
feel.
2 minutes. Give me 2 minutes. I'll just conclude. So this is criterion
Yes, yes.
yeah, I just take a map. Then you take its norm. Norm. You put a norm here, and suppose the series are convergent, and there should be additional assumption that this composition Ts should be identity on the density. So if this condition is satisfied, then T is actually chaotic. So we have this. Sutradhar, am I audible? Yes.
Yes, yes.
So just we will straightforward as an application. We can directly apply this to our shift. What we'll do, twice backward shift is given C times backward shift LP to LP, LP to LP. So we'll take the map as the forward shift x1, x2, so on. That will be the forward shift x. So just shift to right side. One can easily see that beta is equal to identity, which is what we want in the density. And D, the density will take as the set of all sequences with the finite span of the or basis with n greater than or equal to 1. So since elements in D have only finite support, one can easily see that twice B to the power n x will converge to 0. It will be 0 at certain stage for each x in D. And twice E into 1 by 2 S is equal to identity on 2. It's actually C times C. C. Now only one more condition we have to see is the 1 by C power n S power n x is its norm should be convergent. So which is true because S, the norm of S
The speaker has left us again. It is better to conclude the talk. I'm requesting the speaker to conclude the talk. The speaker is trying to connect us. This time, I will request him to conclude.
Today, there is a lot of difficulty in this internet actually, a lot of issue. I have got a class at 1 o'clock. I do not know whether I will be able to take or not.
Yes. The speaker has
Yeah,
joined
so
us
I
again.
think, right. So I think I have concluded. I have stated the main result. Considering the network issue, I think perhaps it's time to wind up.
Yeah. So thank you for this
Yeah.
talk. The audience, do you have any questions? Audience, do you have any questions?
Any questions?
It's okay. No questions. No
No
questions.
questions. Okay.
Yeah. So actually, yeah, maybe I should say I should regret because network issue and all those things. Maybe in a future occasion we can see for a better talk.
Okay. Dr. Anish, I would like to ask a question. Like this theorem, the proof of this theorem is started from taking the function, particular function f equals to z square, right?
Yes, yes.
Uh, so slowly it is proved that it is the proof is extended for the powers of z
Right,
rather
right,
than 2.
right.
Yeah. And my question is that the function f, that is from capital X to capital X,
Yes, yes.
may be any function x.
X.
So
So
is it possible
is
to
it possible
generalize
to
for any
generalize?
function?
No. So this will be, you can generalize this main result, that criterion, etc., to continuous homomorphisms on topological groups, which in particular include Banach spaces in this linear spaces.
Okay.
So maximum to the general setup, you can go is homomorphism. From group theory, we know what it is, what
Yes.
homomorphism
Yes.
is. So on, suppose you have a continuous homomorphism on a topological group, separable topological group, then this result hold.
Okay. So
So
thank you, Dr. Anish.
Yeah, yeah. So maybe I should
Uh,
thank, and also maybe in a future occasion we can see for a better talk. Thank you, and thanks
yes. Yes.
for
Sure.
inviting me for this talk.
Yeah. So I shall express a vote of thanks. So thank you, Dr. Anish, once again for enhancing our knowledge on understanding the correlation between complex analysis and linear algebra through this valuable talk. Our thanks are due to the colleagues, research scholars, and students in the audience. And our big thanks go to Dr. Manoj Ranjan Naik, the Honorable President of Siksha Anusandhan deemed to be University, who has been always a source of inspiration to all of us. And I extend our thanks to Professor Manjula Das, the head of Center for Applied Mathematics and Computing, for the necessary supports. And lastly, on behalf of the Center for Applied Mathematics and Computing, Siksha Anusandhan University, extend our heartfelt thanks to all. So thank you once again, the speaker and our colleagues. Thank you all, and thank you the students, the research scholars. Thank you. Hereby, I am officially ending the recording and video. Thank you.
Okay, so Sutradhar, then can I leave then?
Yes, yes. Thank you.